Welcome to Code with Vinay. In this video, I'll be covering K-Maps with respect to ISC syllabus. You can see the relevant portion of the ISC syllabus on the screen. As per the syllabus, students should be able to reduce Boolean expression of up to 4 variables using K-Map. Other terms mentioned in the syllabus are mostly terminology, which the student must be aware with in order to understand K-Maps. Let us understand these terms before we can actually begin reducing Boolean expressions through K-Map. K-Map is a graphical approach to reduce Boolean expressions. This tool was introduced in 1953 by Maurice Karnaugh, and hence the name K-Maps. The first term which we must know of is a literal. A literal is a Boolean variable or the complement of a variable, meaning A is a literal as well as A complement is also a literal. The next two terms which we must be aware of are minterms and maxterm. The product of all literals either with the complement or without the complement is known as minterm. For example, A dot B complement is a minterm, A dot B is also a minterm. The sum of all literals, on the other hand, either with complement or without complement is known as maxterm. For example, A plus B complement is a maxterm and A plus B is also a maxterm. SOP stands for sum of products and is represented by the Greek letter capital sigma, whereas POS stands for product of sum and is represented by the capital pi. SOP and POS are both methods of representing Boolean expressions. The main difference between SOP and POS is that SOP is a way of representing a Boolean expression using minterms or product terms, while POS is a way of representing a Boolean expression using maxterms or sum terms. Now, a single variable, let's say z, can assume two possible values, either a 0 or a 1. Similarly, if there are two variables, let's say y and z, each of these two variables can assume two values, 0 and 1. So for two variables, the total possible values which they can assume together is 4. Similarly, if there is a third variable, let's say x, that can also assume two values, 0 and 1. And for three variables, the total number of possibilities are 2 into 2 into 2, that is 8. Similarly, for four variables, let's say w, x, y, and z, each of these two variables can assume two values, 0 and 1, and hence the total number of possibilities now in case of four variable is 2 to the 4 to the 8 to the 16. And this is a very important thing. Why? Because a 2 variable K-map requires 4 cells, a 3 variable K-map requires 8 cells, and a 4 variable K-map requires 16 cells. Now let us see how this information fits together. Now, in this table, I have enumerated all the possibilities of 2 variable expressions. Notice 0, 0, 0, 1, 1, 0, and 1, 1. Each row of the table denotes one possibility. Now, please convince yourself regarding this statement. It may appear that there might be more possibilities, but note that in Boolean algebra, by commutative law, the order of variables for an operation do not have any impact on the result. For instance, x plus y is same as y plus x. Hence, there are only 4 possibilities for a 2 variable K-map. Now let us focus on the third column, that is this column, which lists product terms or minterms. Here I want you to notice that we are complementing a variable when there is a 0 and the variable is being used as it is when there is a 1. Please notice here x is 0, so we are complementing it, y is also 0, so we are complementing the variable y. In the third case, x is equal to 1, we are using x as it is, and when y is equal to 0, we are using y complement. The fourth column in this table depicts the notation for representing the minterms. A small m followed by a numerical subscript is used to represent the minterm. So just to give you a recap, when x is 0, y is 0, we take the complements, that is x complement, y complement, and this is being represented by m0, where 0 is actually the binary equivalent. 0 0 is 0. Similarly, if you see the third case, we are writing m2 over here, and the corresponding value of x and y is 1 0. 1 0 is 2 in binary. So that's how it goes. Now let us talk about max terms or sum terms. The first two columns are same as before and list all the possible values which the two variables may assume. The third column is for sum terms or max terms. Note the plus in between. The fourth column is for the notation, and the notation for the max term is a capital M followed by a numerical subscript. Note that Minterms was represented by a small m, whereas max terms are represented by a capital M. Now the same concept will apply to 3 variables as well as 4 variables. The only difference is that the number of rows over here will increase, that is the number of possibilities which the variables may assume will be more. So here in case of 3 variables, there are 8 minterms and the notation is m0 to m7. Similarly for max term, in case of 3 variables, we have a plus over here and the notation is capital M, and it starts from m0 and goes till m7. And for the fourth variable, obviously there will be 16 possible combinations, so m0 to m15. Now a Boolean expression can be expressed in a canonical representation or using a cardinal representation. So there are 2 representations, canonical representation and cardinal representation. Canonical representation means that the entire expression will either be in max terms or min terms, whereas cardinal expression means that we use numbers to represent the individual terms. Let us understand this further with the help of an example. So let us say we have a Boolean function of 3 variables, f of x, y, z. And let's say those 3 terms are this one, and this one. So we'll say is equal to x complement dot y complement dot z complement plus x complement dot y dot z complement plus x complement yz. So this is the canonical form. All the terms are having all the literals and it is in sum of products form. The same can be represented by using the cardinal representation, that is we'll use sigma for this because this is in minterm, and then we'll give the numbers, that is 0, 2 and 3. So this is an example of an SOP form. The first one is the canonical form and the second one is the cardinal form. Now let us take an example in POS form as well. So we'll take another expression this time of 3 variables, and let's say we are considering that this time the terms available to us are this, 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 this and this. So let's have a canonical form first. X plus y plus z complement, that's the first term, and then we'll have a dot because this is product of sum. Next one is x complement plus y plus z, x complement plus y plus z, then that is followed by x complement plus y plus z complement, and then the next term, that is 1 2 3 4th term, x complement y complement plus y complement plus z, and finally x complement plus y complement z complement. So this is our expression in POS. Now if you want to represent the same thing using the cardinal notation, then we'll use pi because this is POS, product of sum, and the terms are 1, 4, 5, 6 and 7. 1, 4, 5, 6 and 7. Another thing to keep in mind is that SOP and POS forms are complement of each other. So for example, if there is a 3 variable expression f of x, y, z, the number of possibilities in this case is 8. So if sigma of this is equal to, let's say, 0, 1, 2, 5, and we want the pi version of it, that is the POS, then what we have to do is we'll just take the missing term. So 0 is over here, 1 is over here, 2 is over here, 3 is not there, 4 is not there, 5 is there, so we leave a 5 out, then 6, 7. So this is the relationship between the sigma and the pi version. So in the worst case scenario, let's say in the examination you are given the expression for pi and you're asked to do it for sigma, or the other way around, this is how you do it. In order to use K-map, the expression must be in canonical form. If it is not in canonical form, we have to convert it into canonical form first, and after that only we can apply K-maps to it. For example, let's say we have an expression of 3 variables, let's say x, y, z, and the terms are x, y, z plus x, y. Now notice that there is no z in the third term. Now we just cannot write z directly. So what we have to do, we'll say that x dot y dot z plus x dot y dot, and then we'll say dot 1. Please note, when you say dot 1, the original value of the term is not going to change because a dot 1 is equal to a. And then what we'll do is we'll substitute, instead of 1, we'll substitute z plus z complement. That is, whatever the missing term is, we'll say that missing term plus missing term complement. And then when we'll expand it, that is x dot y dot z plus x dot y dot z plus x dot y dot z complement, and now the expression is in canonical form. So this is how you will convert an expression into canonical form if it is not already in canonical form. For converting into a POS form, instead of saying dot missing term plus missing term complement, we'll say plus missing term dot missing term complement. Now let us discuss sum of products reduction using Karnaugh map. In sum of product reduction, each square of K-map represents a minterm of the given function. That is, for a 2 variable K-map, 2 to the power 2 is equal to 4, hence there are 4 squares. For a 3 variable K-map, 2 to the 4 to the 8, that is 2 to the power 3 is equal to 8, and hence we have 8 squares. And for a 4 variable K-map, 2 to the power 4 is 2 to the 4 to the 8 to the 16, and hence we have 16 squares, 1 for each minterm. Now, a K-map can be labeled in many ways, but we'll be using the most popular form, that is the one which is used in most of the books at 11th and 12th level. For a 2 variable K-map, let's say f of xy, we'll take x on the vertical axis and y on the horizontal axis. For a 3 variable K-map, let's say f of x, y, z, we'll take x on the vertical axis and y and z on the horizontal axis. And for a 4 variable K-map, let's say f of w, x, y, z, we'll take wx on the vertical axis and yz on the horizontal axis. Now let us label the individual rows and columns. So the first column is for y complement, second column is for y, the first row is for x complement, and the second one is for x. Similarly over here also, the first row is x complement, second row is x, and on this horizontal axis, the first one is y complement, z complement, second one is y complement, z, third one is y, z, and fourth one is y, z complement. For the 4 variable K-map, we have wx on the first column. So this is w complement x complement, then we have w complement x, then we have wx, and that is followed by wx complement. On the horizontal axis, we have y complement, z complement, y complement, z, y, z, and yz complement. Now let us number these cells. So x complement y complement is 0, 0, which is simply 0. X complement y is 1, so we write 1 over here. X y complement is 2, that is 1, 0. Remember, uncomplemented variable in SOP is 1 and complement is 0. And the last cell xy is 1, 1, which is actually 3. The same thing goes over here in the 3 variable K-map. So this will be 0, this will be 1, this will be 2, this will be 3. Similarly, this will be 4, this one will be 5, this one will be 6, and this one will be 7. And in 4 variable K-map, the numbering will follow the similar pattern. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now let us also see the labeling and numbering of the cells for POS reduction using K-map. Since POS is the complement of SOP, the labeling will also be the complement of SOP. So where the variable was complemented, here it will be uncomplemented. Where it was uncomplemented, here it will be complemented. So say for instance, in the earlier one, we had x complement x. Here it will be reversed. That is, we'll have x followed by x complement. Similarly here also, in the earlier one, we have y complement y, but here it will be y complement. The numbering, however, will remain the same. That is 0, 1, 2, 3. The same goes for the 3 variable K-map as well. The numbering will remain the same. So 0, 1, 2, 3, 4, 5, 6, 7. But the labeling will be complemented. That is, here we'll have x, here we'll have x complement, here we'll have y plus z, and here will be y plus z complement. Here we'll have y complement plus z complement, and the last one will be y complement plus z. The same pattern will be followed in case of 4 variable as well. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and the labeling will be the complement of what we had in SOP. That is w plus x, w plus x complement, w complement plus x complement, and w complement plus x. The same goes over in the horizontal axis. So here we'll have y plus z, y plus z complement, y complement plus z complement, and finally y complement plus z. So this is how we label and number the K-map in POS form as well as SOP form. Now we'll see how we can plot the K-map. So we'll start with the smaller one. So here we have a function of 2 variables x and y, and the terms mentioned are 1, 2 and 3. So when we have a sigma, that is sum of products, we'll use 1 to plot the K-map. When we have pi, then we'll use 0 to plot the K-map. So in this case, this is sigma. So what we'll do is we'll plot it by 1. So we'll have a 1 on the cell numbered as 1. We'll have a 1 on the cell numbered as 2, and we'll have a 1 on the cell numbered as 3. Now, in case we have a POS K-map, then what we'll do, we'll mark it with a 0. So in this case, the function of xy is pi of 0, 1, 2. So in the cell 0, we'll have a 0. In the cell 1, we have a 0. And in the cell 2, we'll have a 0. The procedure will remain the same, whether it's a 2 variable K-map or a 3 variable K-map or a 4 variable K-map. Only the size will change, and sigma is 1, pi is 0. Now let us also plot a 4 variable K-map. 4 variable K-maps are important from the examination perspective because these are the ones which are mostly asked. So we have a function f of 4 variables w, x, y, z, and the expression is in the sigma form. That is, we'll mark it by a 1. So we'll have to mark 1 at the 0 cell, at 1, at 5, at 7, at 8, 9, 10, 11, then 12, 13, 14 and 15. So this is how we plot. For reducing the expression, first we have to mark pairs, quads and octets. A pair is a group of 2 cells. A quad, as the name suggests, is a group of 4 cells, and an octet is a group of 8 cells. So in this case, this is a pair, that is a group of 2. This is a quad, that is a group of 4, and this is an octet, that is a group of 8. An important point to note over here is that a pair removes 1 variable, a quad removes 2 variables, and an octet removes 3 variables. The idea of using a K-map is that we want to reduce the expression and we want the maximum reduction, and that can only be achieved if we first try to form an octet. Once we have formed all the octets, then we moved on to forming a quad, and once all the quads have been identified, then we'll move on to forming a pair. Another point to keep in mind is that we have to form the least number of groups possible. That is, we'll not be marking pairs inside a quad and octets, or quad inside an octet. This is not to be done. Similarly, this is not to be done, and similarly this is also not to be done. So no smaller groups within bigger groups. Our objective is to identify bigger groups first, followed by smaller groups, while keeping in mind that groups should not be nested, and that is, avoid a group which is completely inside another group. Let us have a look at another example. So if you are thinking that there is an octet and a quad, then you are wrong. We have to first form the bigger groups. That is, there is an octet over here, and there is another octet over here. And since bigger group leads to more reduction, these 2 octets will remove more variables than an octet and a quad. And remember that we always try to make the biggest group possible. So for example, if we have a 1 over here also, then don't think of forming a pair like this or a pair like this. What needs to be done is that we'll try to form the biggest possible group. That is, now we'll make a quad over here, which will lead to reduction of 2 variables. Another important thing that we must be aware of is redundant groups. A redundant group is a group of ones or zeros whose all members are overlapped by other groups. We don't consider redundant groups while writing the simplified equations from the K-map. For example, if we have a 1 over here, a 1 over here, a 1 over here, and a 1 over here, while grouping, what we'll do, we'll make this pair, we'll make this pair, and we'll make this pair. And now if you notice, the pair over here, that is this one, in this case, both the constituents, that is the first one is the part of this pair and the second one is a part of this pair. Hence this group, that is 1 5, is actually a redundant group, and we'll not consider this while simplifying the expression. Why? Because this will lead to extra variables. Ideally, one must avoid marking the redundant groups, and it is a good practice to look for redundant groups once you have identified all the groups before proceeding to the simplification step. Now let us have a look at another interesting case. So the usual thought process is we try to make the biggest group possible. So the first thing which we make is a quad, and then we make 4 groups. And why is this case interesting? Because the moment you make 4 groups, you'll realize that the quad is now redundant. All the ones of the quad are already used in the pairs. So in this case, the correct grouping is that you only have to form the pairs and not the quad. So like I said, ideally you should avoid this, but in cases like these, it's difficult to avoid these. So what you can do is you can say that the group M5, M7, M13, M15 is redundant. But if you are alert, making 4 pairs in the beginning obviously looks neater, and obviously this is the correct answer as well. Now before we can move to the last step, that is the actual simplification step, there is one more thing to discuss, and that is rolling or wrapping up of K-maps. Imagine bending a rectangle, that is the K-map, in 3 dimensions onto a torus. What it means in simple terms is that the ones or the zeros on the sides will be next to each other if one imagines that a K-map has been rolled. Like here, these ones on the sides will get next to each other when you think of it as a rolled K-map. And that is why these ones can be treated as a quad. The same thing will happen in case of a corner ones, in case of a 4 variable K-map. Like say for example here, these 4 ones, the ones on the sides, you can imagine this fold up like this, and then again these ones are on the sides. So the ones on the sides, or for that matter 0 in case of a POS K-map, can be treated as a quad. The most important thing in the K-map is the arrangement of cells. Notice that whenever we move from a cell to the adjacent cell, that is the cell just next to it in the horizontal or vertical direction, only one variable changes state. So let us focus on cell 5. Cell 5 is W complement X and Y complement Z. The cells adjacent to the cell 5 is 4, 1 and 7. Now let us consider these 2 cells for example. In these 2 cells, that is cells 4 and 5, W complement X is common to both, but if you see this axis over here, Y complement is same but Z is changing the state. Similarly, if we consider 1 and 5, here Y complement Z is same but over here only X is changing the state. Similarly, if we take 5 and 7, here again W complement X is same but Y is changing state, whereas Z is same. If you look carefully, you'll realize that that happens at the corners also. Like for example, if I say 4 and 6, here also W complement X is common to both the cell 4 and cell 6. But if you look at the top, only one variable, that is Y in this case, is changing its state from Y complement to Y, whereas Z complement is same. The same happens in case of 9 and 1. Here y complement z is same, but w is changing its state from w complement to w, and that is why, that is also one of the reasons why the wrapping or rolling up of the K-map works. Even if we move this first column to the end, or the last column to the beginning, or the first row to the end, or the last column to the beginning, if you move from one cell to the next, only one variable will change its state, and that is a very important thing. So if we have a 1 over here, over here, over here, over here, and over here, we can form a quad out of these 4 ones, and we can also form a quad out of these 4 ones. Now let us see how we can reduce the individual groups. We'll start with the pair. So let's say we have a pair over here, 1 over here, and a 1 over here, and this will form a pair. Now in order to reduce this, we'll look for the variable which is changing its state. So if you look over here, w complement x complement is not changing. This is common to both of these cells, but at the top y is changing its state from y complement to y, and hence y will be dropped. So we'll say that the pair represented by m1 plus m3 is equal to w complement dot x complement dot z. So the core idea is that whichever variable changes its state, that is dropped. Let's say there is another pair over here. So now what will happen? We'll form this pair, and this pair will be referred to by saying pair m3 plus m7, and in order to reduce it, we'll see what is changing the state. So y dot z is common to both. That's not going to change, that will remain there. But if we see over here, x complement is changing into x, so x will be dropped. W complement yz will be the reduced expression for this. So w complement yz is the reduced expression. Now we'll see how to reduce a quad. So let's have a quad first. So let's say our quad is over here. We'll form a quad, and in order to refer to this quad, we'll say quad m5 plus m7 plus m13 plus m15. So on the vertical axis, w is changing state, so w will be dropped, x will be retained, so we'll get an x over here. On the horizontal axis, y is changing the state, z is not changing, so z will be retained and y will be dropped, so this will be x dot z. Now let us see how we can reduce an octet. So for octet, we'll need a group of 8, so let's have 8 ones, and then we'll form an octet. Now this octet will be represented by m1 plus m3 plus m5 plus m7 plus m9 plus m11 plus m13 plus m15. And if you notice over here, on the vertical axis, both the variables, that is w is changing states as well as x is changing its state. But on the horizontal axis, only y is changing state, z remains the same. Hence y will be dropped and z will be retained. So this will reduce to z. Now an important point, a very important point, is that an octet is reducing 3 variables, a quad is reducing 2 variables, and a pair is reducing only 1 variable. So notice there were 4 variables w, x, y, z, out of which 1 was reduced. In case of a quad, there were 4 variables out of which 2 were reduced, and in case of an octet, there were 4 variables out of which 3 were reduced. And that's why we prefer an octet over a quad and a quad over a pair. There is one more point which I would like to emphasize, and that is a K-map may have multiple valid solutions. For example, take a look at this configuration. I have a 1, 1, 1, 1 over here, and 1, 1, 1, 1 over here, and there's another one over here. Now, we cannot form an octet because these ones are not close together, but we can form a quad over here, and we can form a quad over here. Till now everything is straightforward, but now this one, that is cell number 5, you may club it with this, but you may club it with the other side also. And please note, you cannot club both of them together because then this becomes, one of these groups becomes redundant. So the point which I'm trying to make right now is that either you will club this one with the one on the left, or you will club this one with the one on the right, and both of these will lead to a valid solution. Now we'll be solving a few questions to reinforce these concepts in your mind. Let's begin. The first step is to plot the ones. So 4, 5, 8, 9, 10. 4, 5, 8, 9, 10, followed by 11, 12, 13, 14, 15. That is 11, 12, 13, 14, and 15. Here the idea is we'll try to make the biggest group first, that is we'll try to make an octet, and there is an octet over here. So our first group is going to be this octet, and then we'll try to form a quad, and we can form one quad over here. The next step is reducing these groups, so let's do that also. So we'll first reduce this quad, so we'll say quad, and then this quad will be represented by saying M4 plus M5 plus M12 plus M13, and let's see what it reduces to. So on the left hand side over here, we can see that W is changing the state, X is same, so we'll take X from this side. From the top we'll see that Z is changing state, Y complement is same, so we'll take Y complement. Now let us proceed on with the octet. So we'll say octet, and then we'll mark the octet first. So this octet will be represented by M8, M9, M10, there has to be a plus in between, plus M11, plus M12, plus M13, plus M14, plus M15. Now on the horizontal axis, all the variables are changing their state, but on the vertical axis only X is changing the state. So X will be dropped, all the variables on the top will be dropped, and only W will be retained. So this will be W. So the final answer over here is X dot Y plus W. Let's try another question. Let us begin by plotting the ones. So 0, 1, 2, 4, 5, 6, 0, 1, 2, 4, 5, and 6, followed by 8, 9, 12, 13, 14, 8, 9, 12, 13, and 14. And the usual step, we'll first try to make the biggest group, which is an octet in this case. So let's make that octet first. So we'll have an octet over here, and then we'll form two quads, one over here by rolling the K-map, and the other one also over here by rolling the K-map. Now let's proceed with the actual reduction of these groups. So I'll first reduce this quad over here. So we'll say quad 1, and our quad 1 is 0, 2, 4, 6. M0 plus M2 plus M4 plus M6, and let us see what it reduces to. So if we look over here, X is changing its state, W complement is same, so we'll take W complement. And if we look at the top column, y is changing the state, but z complement is same, so we'll take z complement. Let us move on to the next quad over here. So we'll say quad 2. Then we'll identify the quad 2, and this time it is M4, M6, M12, M14. M4 plus M6 plus M12 plus M14. And if you look over here, this time W is changing the state, so X will be taken over here. And if we look at the top, again the same thing will happen because the same two columns are involved. Y is changing its state, but Z complement is not changing, so we'll take Z complement over here. Now the last one is the octet. We'll first identify our octet, and that octet is M0 plus M1 plus M4 plus M5 plus M8 plus M9 plus M12 plus M13. And local axis is changing, that is both W and X are changing their state, but at the top column we'll see that Y complement is not changing, Z is changing, so we'll take Y complement. The final answer would be, in this case, W complement dot Z complement plus X dot Z complement plus Y complement. Let's try another one. Again, we'll begin by plotting the ones. So 0, 2, 6, 8. 0, 2, 6, 8, 10, 14. 10, 14. So there are two quads over here. One is this vertical one. So let's mark the vertical one first. So this is one quad. And the other quad will be obtained by rolling the K-map. So there is another quad over here. Let's do the reduction. So I'm treating this vertical quad as quad 1. So we'll say quad 1, and then we'll identify the quad, and that is M2 plus M6 plus M10 plus M14. And this is going to reduce to simply Y dot Z complement because everything in the vertical axis is changing the state. So we'll say that this will reduce to Y dot Z complement. Let's talk about the other quad, which is formed by taking the corner ones. So we'll call it quad 2. Let's identify the quad. So M0 plus M2 plus M8 plus M10. And if we notice on the sides over here, W is changing the state, X complement is same, so we'll take X complement. Now we'll see on the top over here and here, Z complement is same and Y is changing, so we'll take Z complement. The final answer will be Y dot Z complement plus X complement dot Z complement. Let us move on to the next one. Let us begin by plotting the ones first. So the numbers are 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. Followed by 11, 12, 13, 14, 15. 11, 12, 13, 14 and 15. Now let us form the groups. The biggest possible group is an octet over here. And then we can form two quads like this and like this. Step. So I'm calling this squared, that is 5, 7, 13, 15 as squared 1. M5 plus M7 plus M13 plus M15. And in order to reduce it, we'll first concentrate on the left hand side. Here W is changing the state, X is same, so we'll take X. And on the top, Y is changing the state, Z is same, so we'll take Z. Let's move on to the next squared, that is this one. So we'll first identify the quad. We'll say M7 plus M6 plus M14 plus M15. And on the side, the situation remains the same. W is changing the state, X is same. And on the top, Z is changing the state and Y is same, so we'll take Y. Let's move on to the octet. We'll first identify the octet, and our octet is M8 plus M9 plus M10 plus M11 plus M12 plus M13 plus M14 plus M15. And everything on the horizontal axis is changing, but on the vertical axis over here only X is changing, so we'll take W. The final answer in this case is X dot Z plus X dot Y plus W. Now we'll solve some product of sum questions. And in POS we'll mark zeros. So 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 8, 9, 10, 11, 8, 9, 10 and 11. So let's see the groups. We can form an octet over here by rolling the map. And once that is done, we can form one quad over here. Let's proceed on to the reduction part. So we'll say quad, and then we'll identify our quad. So it is, sorry, this has to be capital M. So M0 dot M1 dot M4 dot M5, and this will reduce to, over here X is changing, so W will remain, and at the top Z is changing, so Y will remain. That is one. Then we move on to our octet. Let's identify the octet first. So M0 dot M1 dot M2 dot M3 dot M8 dot M9 dot M10 dot M11, and this will reduce to, let's see, everything on the top axis is changing, but between this row and this row W is changing the state, so W will be dropped, and X is same, so X will be taken. The final answer will be W plus Y dot X. Let us now move on to the next POS question, and we'll begin by marking the zeros. So 3, 4, 5, 7, 3, 4, 5, 7, 11, 12, 13, 14, 15, 11, 12, 13, 14 and 15. Let's confirm. 3, 4, 5, 7, 3, 4, 5, 7, 11, 12, 13, 14, 15, 11, 12, 13, 14 and 15. Now in this case what we'll do is we cannot form an octet because we don't have sufficient number of zeros at one place, but we can definitely form 3 quads. Let's see those. This is our first quad, the vertical one. This is our second quad, and then this is going to be our third quad. Let's move on to the reduction. So we'll say quad 1. I'm treating this vertical quad as quad 1, so we'll say quad 1 is M3 dot M7 dot M11 dot M15. Now everything in the vertical axis is changing, so we'll take y complement plus z complement. Let's move on to our second quad, which is this one. So that will be identified by M4 dot M5 dot M12 dot M13. And let's see the reduction. W is changing the state, x's complement is same, so we'll take x complement. And on top, y is same, z is changing, so we'll take y. Let's move on to the third quad, and third quad is identified by 12, 13, 14, 15. 12, 13, 14 and 15. And here everything on the top is changing, but here what is common is w complement plus x complement. So w complement plus x complement. The final answer will be y complement plus z complement dot x complement plus y dot w complement plus x complement. And now we come to the last question of this video. Again, we'll begin by marking the zeros. So 0, 1, 2, 3, 5, 6, 7, 10, 14, 15. And the grouping will be, there is one quad over here, there's another quad over here, then we can make one more quad over here, and finally another quad over here. So quad 1 is our horizontal quad, so we'll say quad 1. We'll identify the quad, we'll say M0 dot M1 dot M2 dot M3. And this quad will reduce to w plus x because other variables on the top are changing their state. So this will be w plus x. Let's move on to our next quad, and that quad 2 is the vertical quad which we made. That will be identified by M2 dot M6 dot M10 dot M14. And again, everything on the vertical axis is changing, so we'll take y complement plus z. So this will be y complement plus z. Now we move on to our quad 3, which is the one over here, that is M1 dot M3 dot M5 dot M7. Let's see what it reduces to. So over here on the vertical axis, x is changing the state, so x will be dropped, we'll take w. On the horizontal axis, y is changing state, z complement is not changing, so we'll take z complement. Let's move on to the last quad, that is quad 4, and that is identified by 7, 6, 14, 15. M6, M7, M14 and M15. And if we see the reduction, W is changing state, X complement is not changing its state, and at the top Z is changing, Y complement is not changing, so we'll take Y complement. The final answer will be W plus X dot Y complement plus Z dot W plus Z complement, and finally X complement plus Y complement. I hope that you found this video useful. If you have doubts or clarifications, please feel free to use the comment box below. That's all for now. Thank you. Your feedback is valuable to me. I want to make sure that my videos are clear and helpful. If you have any questions or suggestions for improvement, please don't hesitate to leave a comment or send me a message.